Hi, good morning. Okay, today I will introduce the chapter 15. Chapter 15, we are talking in general about laws of thermodynamics. My first focus is going to be on the first law of thermodynamics. And the first law of thermodynamics, it is, using another way to express conservation of energy. And that is, we are talking about conservation of energy in thermodynamic systems. Now, it's stating that delta U equals Q minus W. There are many forms of this first law of thermodynamics. You're going to find them, different forms. The one that I want you to solve and the one that I want you to adopt is the one that I have in here, which is the one in our textbook. These are my definition. Delta U, it is change in internal energy and it is measured in joules. And we're going to talk about how we're going to calculate the change in internal energy. Q, it is the net heat transfer or the net quantity of heat transferred, and this is in joules. And W is the work done by the system, not on the system. All right, this is very important. Now, delta U, we're going to see that it depends on the state of the system. Then it depends on final and initial temperatures. Only it has nothing to do with the bath. And I will explain in a little bit what does that mean. And but when we talk about work and heat, they depend on the actual path that you are taking. Um, all right, let me explain this here. Okay, it's better if I will explain it here. Let's assume this is my P, whatever unit I'm going to use, B versus V, let's say liters. Okay, any unit, the unit here is not going to be important. Now, I can say, okay, like my system maybe add this here A, and then it's gonna go to B, which is here, and then it's gonna go to C, which is here. Now, and of course, my system can go directly this way. Okay, I will say the work and okay, the work W and Q, which is quantity of heat. They depend on the actual bath, which means going A to B to C is different. They're gonna give you different values for Q and W. It's different from going from A to C. Okay, but in all the cases, delta U CA or like UC minus UA is going to be a constant. Okay, whether you took ABC or AC directly. Okay, then this is something that you need to know. Now, I'm gonna define in like a kind of processes that we are going to be having like a familiarity with, and these I will say like they serve as if they are what is called keywords. Okay, the first one is isothermal process, and when it is isothermal means the change in the temperature equals zero. And we said U is depending on temperature, then U is going to be constant, and therefore delta U be 0. And then I can say here that like the first law of thermodynamics, delta U, which is Q minus W. Now this number here, or this quantity, is going to be 0. Therefore, I can write this in this form. Then in an isothermal process, delta U is 0, and if you calculate, the work done is gonna equal to Q. The next one, it is isobaric process. Isobaric process means it is constant pressure. When we will draw this into the, I forgot to tell you now how we're gonna graph this. I'm gonna also talk about it later, but this is P versus V, and that one here we call it isothermal, the line, okay? The temperature is constant over this. Now, for constant pressure, we're gonna have horizontal line like this, and if we can say always that the work done is area under the curve, and for this one here, W equals negative P times delta V. P, it is the pressure, and delta V is the change in volume. The next process here, isochoric. Isochoric means constant volume, and if we want to graph this one, when we graph isochoric, we are going to find that it's going to be a straight line like this. Now, what's the area under the curve here? Of course, it is 0. There is no area on the curve because it's a vertical line. And therefore, when I have the delta U equals Q minus W, if this number now is 0, then the change in the internal energy will equal Q. The next process, it is adiabatic process, and the adiabatic process, the system is isolated. Okay, then my system is here, and it is isolated. It cannot interact with the outside, then Q is 0, and my delta U equals Q minus W is gonna be, okay, like this. Now, one thing that I want you to know, that if I have PV diagrams, and this one is the isothermal, the adiabatic is gonna be something like this. It's steeper. Then this can be adiabatic, and that one is isothermal. You need to be able to differentiate between the two. Okay, here some of the examples that I have prepared for you. What is the change in internal energy of a car? If you put 12 gallons of gasoline into its tank, the energy content of gasoline is 1.3 10 to the 8 joules per gallon. All other factors such as the car's temperature are constant. Now, the energy content for the gasoline, it is 1.3 joules per gallon. Then if you filled up with the 12, then the total energy is going to be 1.3 10 to the 8 times the 12 gallons. And then it's going to be 1.6 10 to the 9. And this is added internal energy to the system as 1.6 10 to the 9 joules. Now, example 2 here. What is the change in internal energy of a system which does 4.50 10 to the 5 joules of work while 3.00 10 to the 6 joules of heat transfer occurs into the system, and 8.00 10 to the 6 joules of heat transfer occurs to the environment? Okay, here delta U is not known. W is 4.5 10 to the 5 joules. We have Q in and Q out. Q into the system 3 10 to the 6 and Q out negative 8 10 to the 6. I need to find what is the net Q, and therefore I added both. Okay, remember when it is out, always is going to be negative, when in is going to be positive. And therefore the net is going to be negative 5 10 to the 6 joules. Delta U, it is Q minus W, and delta U will be negative 5 10 to the 6 minus 4.5 10 to the 5, which is going to be giving me a total of negative 5.45 10 to the 6 joules, which is a net decrease in the internal energy of the system. Here, calculate the network output of a heat engine following path A, B, C, D, A in the figure. Now, for this one here, we're gonna dissect the shape into different areas. Like the first one, it can be this here, which this one, it is called A1. And A1, it is 6 to the 6, okay? This one is not 6, sorry, this is 0.6. Because the base is 2.6 minus 2, then it is 0.6 10 to the 6 multiplied by 1/2. Here, any triangle is going to be 1/2 base times height. Let me explain to you, because here I factored. Then the first one, area 1, it is 1/2 times 0.6 10 to the 6 multiplied by the volume, which is 3. And here, remember, I have the scale multiplied by a number, then you should include it in the calculation. Now, A2, okay, A2 is gonna be, I can say it is this all too. And then it is what is called a rectangular, that is 1 10 to the 6, then the area 2, it is 1 to the 6, yes, that is, I will say length times width times 3 10 to the negative 3 cubic meter. And finally, A3, it is this triangle here, and that is 1 minus 0.6, which is 0.4, 10 to the 6, and of course here I have 1/2 because it's a triangle again, times the 3 10 to negative 3, and then you add all the 3 areas to get what is really the area under the curve. This concludes the first section of chapter 15, which is the first law of thermodynamics.